Welcome everyone for High Performance Computing, Advanced Scientific Computing. Today we have lecture 2 with a conceptual lecture on parallel programming with MPI. Hence, it will demonstrate in generally what MPI can do, a broad overview how this can be done and how it supports parallel programming really with an open standard. And then we have a practical lecture 2.1 where we'll show much more source code examples. We will run together these source codes, of course, in HPC. That means, in other words, we have to compile it. It's mostly C programs. And you will understand a little bit then in this conceptual lecture today, but also then in the practical lecture 2.1, how you parallel program, let's say, and using this, this HPC standard really, what you would call MPI. So before we go into the material of this lecture then, let us review what we have the last time. And the last time was another practical lecture where I showed you a little bit the, let's say, relevance really of C and C++ programs. Why are we talking C, not Java? Why basically Python is just very new in AI applications and has traditionally not played a role in high performance computing, rather C, C++, and maybe even Fortran, right? When you have weather simulations, climate simulations, Fortran is really still used and in many application areas as well. And if you go to these many application areas, they're depicted a bit here if you want with all these ideas here from many different areas of science and engineering. You will see that many of them really have the C and C++ codes in action and also implementations on it. So from the traditional sciences in terms of HPC or that leverage HPC, you would say that would be numerical methods using known physical laws. It would be elements really which are not directly AI, mechanistic modeling perhaps. So different areas where AI is really new, but there's a strong, let's say, user area in HPC of using physics applications, multi-physics applications even, which is quite fascinating. If you think, for instance, here in this groundwater modeling, where you have to understand the groundwater really from different perspectives, you have an atmosphere code called COSMO, for instance, a land surface interaction code called CLM, and then a subsurface really understanding the groundwater with path flow. And that all fits together to understand and simulate what the future will bring. Hence, one important application of HPC as an example that would be scheduled somewhere, because if you remember, the second part of the lecture last time was really on scheduling. Hence, a researcher in Earth system modeling, or here basically in this groundwater modeling, would be perhaps getting one fraction of this HPC joules. At the same time, and this is now the importance of the scheduling, you have this whole UWILS cluster here. You have some nodes that are not really in service. There's a problem. The maintenance is working on it, but the schedule shows there are many different researchers. At the same time, there's a brain researcher using the NEST code, right? If you remember neural networks and spiking, at the same time, there's actually someone exploring earthquakes with a code on this fraction. And there's another one that is doing cutting edge AI and deep learning and machine learning applications with maybe a convolutional neural network or an autoencoder. And these different AI models are also scheduled in different portions here on the HPC system. And this is really the, let's say, lessons learned out of the scheduling, hopefully for all of you. These are the modus operandi of a shared HPC system, which is very large. There are many, many GPUs. In Juwel's booster, we're talking about around 4,000 GPUs. They are not just used always with one person, with one researchers, or even one research group. Hence, this needs to be shared. And in order to share this effectively, also thinking about backfilling, the scheduling algorithms we heard, first come, first serve. But if there's a hole in the schedule, if there's space enough for a job that can be, even if it has been submitted very late in comparison to many others waiting, but if it fits now on the HPC machine, why not using it, right? Which is the concept of backfilling, if you want. It's not really unfair because it doesn't block anyone, but you use the resources. And this is a key paradigm also. If you think about scheduling, they want to utilize HPC resources to the maximum degree. So we're talking about that HPC resources should be in the utilization around 89%, 99%. 100% will be never achievable. You see as this already, right? Because here, for an example, some of the hardware will not follow suit. There's always maintenance somewhere. 100% is hard to get, but the HPC systems and the administrators and the centers that offer these systems strive always to the best utilization to get the best out of taxpayers' money. And the similar situation is in the data centers, right? Commercial data centers that want to have a long uptime, also want to satisfy their users, and of course have their hardware used to the maximum degree to also earn money from the customer. So this is going into the segment more of cloud computing and big data, where we talk about this more in detail. But then this is an important part to think about as well. So this was sort of the idea of, let's say, putting C++ programs in place and also thinking about scheduling. But we also had a practical lecture. And we have seen that basically doing this with a very simple Hello project or source code in C was not really at all complicated, right? A couple of source code lines. But the more important concept was really not using it like this on the login node, but using the scheduler in order to get access to the compute nodes here on Elia. But the concept is true on Juvels. It has exactly also login nodes. It has compute nodes. It's the same paradigm, just on an order of magnitude of scale. And with this, then you would actually compute your jobs depending on how much resources you ask for in the scheduling script. You can then actually create a speed up is one of the benefits really of using this HPC systems. You see here 16 GPUs in parallel, much more faster. If you use Deep or Jubel's Booster here, different, let's say, HPC systems. But that's why you also want to have more and more compute nodes in order to have access to more and more GPUs. Now, if you want to do this to the extreme and say, well, you cannot here, have better speed up, but maybe in many other applications you can. This is just one example of one of our papers here. You always can think about, let's have more and more on the machine, but you see also then, of course, you have to share the machine with others, and they have equal requests for resources. And we will come to this back when we talk about lecture 2.1 now, and also later in lecture 6, lecture 7, when we talk about deep learning again. So let's stick a little bit to the idea of scheduling from the practical perspective side. You have seen the source code was not really touched in order to submit the job in changes. So you could always ask basically for more tasks, for more nodes. You just submit the same executable. And this will bring us a little bit of motivation now for MPI. What we have here now, you would program an MPI application to be scalable. And this will be an element coming up now, actually, in this lecture. But it's important to understand the basics in scheduling still, because they will actually be with us almost the whole course. There's just a Jupyter notebook, which is a bit an exception that we will learn in deep learning a little bit. Still, many deep learning codes are also used with job scripts. So don't get carried away with Jupyter notebooks or Google Colab, let's say, things. When you do really, let's say, deep learning at scale with really big real applications, you need HPC at scale. And this is not done with Jupyter. It's rather done with distributed deep learning, things you will learn in lecture 7. However, we learned that this job script is basically also very trivial. It has trivial information starting with this S batch here. It's a separate file from the executable that we have, compiled out of the C code, right? So important differentiation to Python, for instance, we still have to compile C code here. But then we use this compilation in order to do an MP run here. But before we do this, we capture, the essence, what we learned in practical lecture 0.1 of saying, hey, we have this module environments. So we have to have the right environment. And hence we want to use MPI, although admittedly for the last lecture, here we had in 1.1, we could do it otherwise, but this was a preparation for this lecture and practical lecture 2.1 into your assignment. Hence, we stick a little bit to the MPI and OpenMPI 4, and then also the possibility of using then the MPI-CC for compiling to actually also digest, let's say, the MPI statements that we're going to learn today. Finally, and this is another long, feedback to the other lecture, because it's incredibly important to understand scheduling. Otherwise, you will not survive long on a HPC system. That's the final remark. Think about that it's a batch system. You're somewhere in a batch queue, hence the output when you submit, when you, so to speak, submit it and run it, is not given to you on a screen. You have basically remembered you got this in an output file. Depending on your job ID that you get back when you submit this job, you have basically an output file. And this is the essence, what we learned, I think, in practical lecture 1.1, to have a sort of really basic standing now in HPC. So now you're ready. So you can now think about much more how I actually use all of this computing capacity at scale. And when you think about MPI, that's a way to do, or let's say it's one way to do, so that we will cover in the first, really the MPI concepts, the basics, terminologies, what means message passing, what's the difference between point to point, and perhaps also some MPI collectives. So they are very powerful, implemented on a way more tree-based structure, hence they're very also high performant. And as our course suggests, we are high performance seekers, hence this is important for us. There will be some terminologies which have been, let's say, always a bit complicated for students. MPI ranks, what is the world of communicators? This will be coming up also in lecture 3. So I will make the first parts here, let's say some examples, but we will, of course, will reuse this concept then in domain decomposition, which we will learn in lecture 4 and so on and so on. Then, once you have the MPI basic concepts, it's good to think about some parallel programming basics. And some smart students are always asking me, so what's the difference between, the course we had the last time and last year? And here's some difference now that we already include MPI-IO before. If you remember, we inserted some new interesting, let's say, topics into the course. Hence, the situation is that our lectures changing. So basically, you see here that we have already looking a little bit about blocking and non-blocking MPI communication, although some examples will come in the next lectures. We have I/O challenges, which is another important factor. Traditionally was more later in the course, but now we put that all together in order to have more AI, more machine learning, more deep learning for you later. Hence, here is a little bit the compact conceptual lecture today, where we talk about what MPI-IO can do, what the role of parallel file systems is, parallel applications leveraging this, and then basically community standards using HDF, the hierarchical data format, or NetCDF, for instance, as so-called higher level IO libraries. All of these topics, no doubt, especially if you think MPI-IO and higher level IO libraries like HDF or NetCDF can be complete topics of a course, right? MPI is very rich, and we have in Jülich, for instance, trainings that cover the whole week. And similar aspects with 3 days at least of MPI-IO, parallel IO, HDF, NetCDF, and so on. So obviously what I can bring across here in the course are really basics, as it suggests here in the outline. But afterwards, you still have, I think, a little bit understood the complexities of parallel programming, why it is a little bit different than just programming a little bit in Java. And basically, the different abstractions that you see on different various levels will be also addressed. So we have computing, we have data between compute entities from memory, for instance, as message passing elements, but also the I/O elements, right? So if computing is done, we also want to think about what happens to the data that has been computed, or which data I actually need to compute. Can be in both directions. And with this, you will see concepts with MPI and parallel IO that have been adopted by a wide variety of scientific and engineering domain applications, right? So you're really ready to understand these concepts in basics. Of course, they using it then in the communities really at scale and with so-called de facto standard ways how to use HDF5, for instance, or how you use NetCDF in several different simulation areas. But you got the concepts and really understand how that works. And with this, you really have a sort of HPC programming paradigm understood and can program in MPI. Of course, our practical lecture 2.1 that will come next will follow suit with some real source code and some real execution, not even mentioning your assignment 1, which will be about MPI and parallel programming. So you will be doing this hands-on. And so with this, you should be able to understand MPI, at least from a certain way. Obviously, again, if you're interested in that, you should rather attend a 5 days course from morning till evening. So before we get started a bit on this, let's see a bit what the difference is between the typical concepts you may already know from your, let's say, university studies in the beginning or wherever you come from the YouTube audience. So we have several concepts, arrays, variables you already know. We have several different languages. C, Python was mentioned, Java, Fortran is still in use in HPC. I was mentioning that. And then you have different implementations of certain standards, of certain concepts. You have the Java C, you have the GCC for compiling. So these are all, let's say, different areas how you deal with serial programmings. And this is something which still remains in a way if you do parallel programming, but if you do message passing, there's an additional complexity and additional elements you have to think about. And this is really about concepts like processes we think now about. We have just not one process with many threads. We have several different processes that we want to work together. And when they want to work together, they have to send and receive messages to exchange data. Or if you want collectives, which we will talk about in the course, something like one processor wants to talk to everyone, for instance. Then there are certain groups. SPMD will be an abbreviation we will learn, single program, multiple data. So these are all elements we will talk about. And libraries, of course, as a key concern here, we will focus now because of the MPI lecture on MPI and MPI init and all of the different facets why MPI init is also so important. And then different implementations of the MPI standards are existing, right? We use OpenMPI, but many others in the system, here's for instance missing Parastation MPI, are using different implementation of MPI. MP is for instance another very popular one. So all of this needs to be a bit motivated. So why I'm talking to you that this is important, why MPI is necessary. You see, for instance, here an application example that sticks with us also through the course a little bit is now, if you think about the wave propagation on the ocean, you have a 3D grid on the coastal ocean here, let's say somewhere in Iceland. Not sure if there are these high waves in Iceland that you can surf here in that scale. Even close to Vik, the Black Beach would not have maybe these high waves, but still, the question here is the time, simulate this over time to understand how the wave propagates through an ocean would be one of the application examples I would put here, because it's really relatively easy to understand that the wave height from, let's say, one point in time going maybe to the next grid in the next area, because that's what we will learn in lecture 3, domain decomposition, right? So how you crunch this big ocean into several different pieces to simulate maybe the wave propagation over time, like shown here, or here more conceptually, right? Over the different time, also over the different location. So this is something what would be a perfect example. And if you want to do this on a large scale, let's say the whole south coast of Iceland, then you definitely need HPC. If you want to do this maybe on a couple of centimeters, you don't need HPC. You can do this easily with scikit-learn or other, let's say, more other computing tools. But if you want to do that at scale and understand the bigger picture, usually what you need is high performance computing, and you would use probably something we call here distributed computing, which MPI, meaning that all this information, the wave height at a certain point in time, at my part, if you know, would say that this domain decomposition, and we will have a whole lecture on it about it in lecture 3. So these grids would be maybe assigned to different processors, right, to compute all the waves at the same point, because there's lots of physics involved. Maybe you want to have the interaction with the surfer as well. So how is this speed of the surfer over time, simulated and predicted? So this is something where there needs to be lots of message exchanges to the other memories of the other processors to understand, well, your wave height was there in this grid. So that means in my wave height, in the next time step, this is important too. Hence, there will be lots of message exchanges to inform the other processors what's going to happen on the different areas. So this is something which we will, go back, of course, also to lecture 3. So in this sense, we cannot teach all in one big lecture, right? Hence a whole week in MPI usually. But we'll try to here focus now on the message exchanges, what messages are possible. Another application example you see here from the eyes carving in one of our research is a similar element now with a video, better understanding perhaps that we have a certain time dimension, right? And this is also alluded here in these arrows, right? So also in the processes, they have a certain time where they run. Over this time, I want to simulate this ocean, and over this time, I want to predict overall with all the processes how the wave height will be, perhaps over all this time, over all these tiles or the locations. Hence, you have a complex problem to solve, and you see with the glacier calving, it's much more complex. Hence, you have a much more deep down workflow, really, what to do in parallel, what to do in serial, what to do in parallel. You see an example, the calving of the glacier here, you see in the video, is 560 cores, right? Lots of computing power, while maybe others parts of the workflow are just more 16 cores, and even some of them can be done in kind of serial run. So this has a relationship to HPC as well, workflows, but we focus here rather on simple starts where basically message passing matters. So in a way, something we talked already in lecture 1, right? We want to now solve this problem really in a cooperative way, and the cooperative way needs the message exchanges, needs essentially different processes to really solve that complex problem. Other application examples you already know from practical lecture 1.1 and before. I talked to you already in the reminder, so I don't want to take much more time on this. We have seen this is, of course, interesting to have here 3 codes, and you see already the domain decomposition illustrated in the different codes. That's the only statement I want to give here. In order to have a really large area here of the region, you rather want to put that in this different interesting blocks, while the blocks then actually are the processors that we have seen abstractly before, and the processors are just thinking about themselves in a way, computing this, but there are message exchanges between them to understand what my neighbors have done as well. So this would be a concept that is quite known in many of the physics engineering applications. And just to contrast it a bit, what you already maybe also know from other courses, there's of course lots of experimental data, right? We observe the nature. Like for instance, you see here a very good example is the birds flying, right? Where we learned then over time from the experiment how to craft aircraft, right? So how we build this, the theory to really have Bernoulli's laws and so on, going over the wings and so on, that in the end will help actually to get the aircraft fly, right? If it's not the major principle. But in the end, what we do in HPC and with many of the simulations is sort of building a bridge, right? So we're building a bridge. We don't neglect experiments, and we also not say theory is not important, but we take experimental data, we simulate it to validate theory. And this is really a common theme in all over parallel programming here, right? And as you can understand, maybe still some things are not understood as well. Like let's say, as everybody knows, we still not have aircraft that flap wings, right? Well, actually, maybe this might be a very energy efficient thing to do, what birds are doing. Hence, lots of things to learn. We model this with many different approaches. This is just one example for, giving also rise to the logo of the course, as you see now, where, let's say, HPC is of utmost importance, not only for letting aircraft fly, also the whole air conditioning, everything within an aircraft with ANSYS, things you will learn actually much more with RASER in the second part, computational fluid dynamics and so on. Not only turbines that you see here, that are of course a masterpiece of engineering, they all require HPC and all use sort of numerical methods based on, known physical laws over time. Let's video suggests here to understand maybe the stress on different wind turbine elements, how can we craft them better, how we can make them greener. It's a big topic these days. And all of that will be also captured much more in 8 and 15 with applications. Hence, I stick here a little bit intentionally in the basics to what MPI can do on itself, how AI then in lecture 6, 7 come. Of course, later the applications will give you more application details. However, focusing only on numerical laws and essentially then, physics, We should also point out that in the last coming years, really, we saw in the last 10 years something like a tremendous momentum around AI, machine learning, deep learning, also data mining, if you want, clustering, classification. This has been a huge element, and I was making the point of it already in the prologue and in the first lecture, so I will not go back to it. Just to let you know that here's a clustering algorithm that is also based on the MPI standard, right? So it has MPI in its source code in order to cluster different elements. Like, for instance, here you see a point cloud of downtown Bremen that has been reclustered then essentially from lasers coming to, some interesting 3D data set to buildings, right? And the same is true for all countries. You see that here in the Netherlands, it's something what one of my ex-PhD students that graduated was doing, creating this HPD algorithm. And you see also then what we do is increasing the number of cores more and more and more. So using parallel computing at scale to really tackle those problems, or you see here the clustering of the brain image. And hybrid remains to be seen in our course. We will see how that materializes when we have then lecture 4 with OpenMP, shared memory, because hybrid here stands for we're using OpenMP, shared memory, together with distributed memory. But of course, here in the course today, we focus on MPI, just to give you some motivation that MPI is really useful when you go to applications. Hence, the whole cluster part in modular supercomputing architectures is sort of created for it. Number crunches using MPI at scale. The cluster module that we learned already in earlier lectures in the deep projects have been a bit, let's say, looked at to and designed in that fashion so that we can really support these applications. And the applications are quite known in all these different areas of sciences you see on the right-hand side. They all have codes, source codes, well-established software based on MPI. So another example, and this brings us again to lecture 3, is of course a race car or the heat dissipation in a room. That's something also we will learn in lecture 3 a bit more. Hence, there's a certain note of programming it. You would say you would always have a good parallelization method, the domain decomposition for short, how to basically think about functional areas, like maybe the different tires of a race car or the chassis and the driver and so on, or basically how you basically create a room and then put the room in different pieces in order to create a heat map that you see here over time simulated, right? So how the heat is basically getting in the room, or how the airflow is changing when you open a classroom, things like that. So, however, that gives me also the important point to say that the domain decomposition will come in lecture 3, right? So hence we give out lecture 2 a little bit earlier in order to start earlier with your assignments and to do practicals, right? One feedback from students, they want to start earlier. Hence, you still need to learn a little bit lecture 3 on the time, right? The problem domain that you want to crush down into little pieces to really use parallel programming. Hence, some of the aspects I will just, tackle abstractly, and we will revisit them in lecture 3. Now, coming back to distributed memory, that's something what I already was presenting. So also here we can go be a little bit faster. We said the distributed memory paradigm actually assumes that you cannot access the shared address space here or so from memory from another processor. So it's not shared, hence distributed. Every time I want to communicate a data element that we store in memory usually, needs to be going over the wire, right, to be communicated. Hence the idea of message passing. You see here one example. And of course, during the time of simulating a race car, there's lots of interactions between the different materials, between the air that you see facing the race car and other issues, like liquids maybe on the road. So this is something where distributed memory is really living from this message exchanges. Hence, there's a standard for it. I also was alluding to this already, where you see a little bit here how that works. You have a memory space of one process that has this variable A23 as an example, and we want to send to someone, that is the second process, this variable. So in order to do this, it's not shared memory. This process 2 cannot just go there and get it, right? You need to send it. Hence, you have a buffer, we will learn later as well, of sending, in this, the 23, and the receiver process needs to actually allocate some space for it in its own memory in order to do so. And only then, once I did the send receive, hence the first message exchange you see here, right, abstractly, you will basically able to do A equals B plus 1, because otherwise you would not even have, basically these variable. So that gives us an interesting thing, because A here in this is called 24, or the value is 24, and here is A 23. Hence the processes are completely, let's say, have their memory space not connected, hence making them distributed, and the message exchange is then the relevant part to do. There are different MPI applications. We use OpenMP in the course. When it is from the technical perspective, you would say that different ways of communicating. It's a communication library with a lot of functions. I would say around 20 are often used, maybe 12 really hardly used, but there are very many nuances of how you can communicate. Hence, we have 500 plus maybe in the standard. And on top of that is even parallel I/O. I was alluding to this, but we will see how that materializes in the second part today, not in the first part. So we focus a bit on the communication aspects, how many processes I want to involve in the communication. It's not always send, receive, as we will learn. And then also thinking about how we can implement this best. And just from the MPI, from the technical perspective, the third element then is the portability. So once you have MPI applications running on one system, chances are that you can relatively easy port them to another HPC system, right? Because we have many of them in the union. You have seen that in your HPC in one of my earlier lectures. There's, Leonardo, Mare Nostrum, and so on. And the idea is bringing us to the portability, hence the idea of a standard. So you have, let's say, computing time on all these different resources, let's say HPC machine A and HPC machine B as a researcher. So it is a shame if you would spend a lot of time of really porting this MPI application. Hence, with MPI and adhering to the standard, using the standard, your chances are much more higher to use, your source code you use on this HPC machine, also on HPC machine B, given your computational time grants. And this is really true, even if there may be different MPI standard implementations, right? So this is also another part. Maybe someone is using OpenMP, others are using ParaStation MPI. But this is one of the benefits also to go to MPI. However, university lectures would also tell you a little bit about what MPI is not. And MPI is not a network library for the internet, right? It's not TCP/IP socket programming, another chat client you want to implement across different hosts within the global internet. So this is really a parallel programming within one machine optimized library, right? It has many scientific engineering abstractions that you use in these applications a lot for mathematics, for physics, for, let's say, condensed representation maybe of data, of parallel data using binary data, not readable data. There's lots of these elements where this is something where you don't really want to use MPI, right? So this is important to show. It's really for good high performance communication within a cluster between computing nodes on one system. And this is something which you need to really understand. Coming now to an overview, again, when we think about typical message passing. So that's now again a kind of more element to the idea I already showed you with this simplified idea. So I think that's pretty obvious. There's one compute node with a processor and memory and sends this data now to someone else in the buffer. That means there's a new 17 arriving at some processor, but his own variable is data 80, right? They all have their own values in that. And hence, this is what we call point-to-point communication, because it's just one other processor involved who has maybe completely other data, want to overwrite this data. Just depends on the application logic. But this is something what we call now point-to-point, and it's important to understand this. However, MPI is not, all about that. We have collective functions, and they are also incredibly used because they save a lot of source code. If you want, you can say this could be also easily implemented with a for loop, send, receive, send, receive, send, receive, right? But the broadcast function has avoided this by implementing an MPI communicator, things you also learn much more in lecture 3, where you can use this communicator to really send the same data item now to all other processors in the same communicator. Hence, this is much more easier to write. It is one call of one function, and you define with the communicator which are the processors that actually should get my data. Broadcast. So we call that MPI broadcast, incredibly often used. Now you can think when you have an array of sort, which is often in data structures in science and engineering, you can say also maybe different weight heights for different tiles or grid parts, then you would scatter them across the different processors. So every processor gets something else to do, right? Which is then the scatter function, MPI scatter. And don't worry if you don't get complete the idea now with the function and so on. Practical lecture 2.1 will be all about examples on broadcast, scatter, gather, which is one of the next. And in the scatter, we have this so-called approach one-to-many, right? So again, all of this data should be scattered one-to-many, this array. Hence, you can also see the inverse, gather. So what we can actually get from all the different processors that maybe have worked the last hour on their own, come to some significant result. And I want to gather this in order to maybe do some other calculation or the next iteration for visualization. That depends again on the application logic, but you can imagine that this is another often used function. And indeed, it's true, gather is often used, and even all gather is one of the keys also today from deep learning, as we will learn in lecture 6 and 7 later on MPI. And finally, here is, let's say, simplified ideas, how to use collectives, how to use MPI. Let's say abstractly is like the reduce operation. This has the additional, let's say, advantage of having some operator with it. So you can specify, for instance, a global sum here, right? You would say, like in gather, I want to be interested what you all have been doing in the last hour and what your data is right now. But I'm just interested in the summary statistics and, having the global sum. And this can already, avoid lots of for loops, adding the values that are received, maybe then again together another loop or an iteration over a whole array. Things like that really makes the source code, let's say, more digestible. It's basically for the programmer's convenience a little bit, if you want, this MPI. And still hiding lots of the complexities, right? As you see here, we just call a function. We're not actually bothering around IP about a URI that I want to contact, a port that I maybe contact to, like in web services or so. This is all basically hidden here, what we communicate by just calling these functions, because the MPI environment, and this will be some things that we learn also in the part 2, the MPI environment already knows certain things about your parallel program. And this is something what we will talk in the second part. However, I want to end the first part also on some other very fundamental aspects, which is for students often a little bit more tricky to understand, but it has something to do with the identity of the processors. Now you can think about that. We have, as an example, you see here, 10 processors that we can use. And they all have their different identity, and we have to know the identity, right? So this is now the idea of using MPI rank. So what processor I am in the bigger picture, right? This would be sort of a way of thinking about it. And you see that the ranks are assigned from 0 to 9, always starting with 0. So it's a very important concept. And with these ranks, you can really, in a parallel program that has always the same source code, right? We will come to this back in practical lecture 2.1, understanding ping pong, my different roles maybe in the process. But you have to have now a way with ranks to differentiate in your source code the different roles. Hence, here's an example. While some of the processors calculate maybe the wave heights, the wave, the stream alongside the river, some others actually have the boat itself simulated and its interaction with water. And other processors, again, maybe calculate the wind, getting, into the sail, and the sail then translate, with communicating to the other communicators how quickly you're going over the tiles. So hence, ranks incredibly important in MPI. We will make the case for it, not only in lecture 3, as it here suggests, we will start with this even indeed already in practical lecture 2.1. And then you see here a little bit, and that will be the last part here really in this lecture 2, part 1. We can be more flexible in this. So there are communicators that then can create different groups. The only one that always remains in the MPI environment is the MPI world, which is a process, or let's say the communicator of all processes, the world of all processes if you want, hence the analogy. But you can create different groups and subgroups in order to streamline communications, maybe between the tiles on the ocean and maybe also on the sailing boat, right? Because they interact heavily and so on. Hence, there will be also different elements of creating subgroups and processes. There's a good summary of all what I said, maybe from a different view of perspective. I think it's also good and incredibly good for you to look that video, and we will continue with the second part of the course in a couple of minutes.